and that forms this intermediate, and importantly, it forms Br₂. In this video, we're going to look at why Br₂ is used in the allylic halogenation mechanism and why we get the regioselectivity that we do. You could almost call this video allylic halogenation. Why though? But why? Why is there Br₂ in this mechanism? Where does it come from? And why do we use the least stable carbon radical resonance contributor in this mechanism? Part of that answer I've already got up here on the board. The Br₂ comes from NBS. I'll explain how in a little bit. We're going to use the propagation sequence for this mechanism to explain both of these questions, where Br₂ comes from and why we get the regioselectivity that we do. In the first propagation step, we form HBr as a byproduct. Remember, the propagation sequence is happening over and over and over again, so we keep making more and more HBr. Remember also that the initiation step happens very infrequently. It's fairly rare for homolytic bind cleavage to occur. The homolytic bind cleavage occurs between nitrogen and bromine in this particular mechanism, so this doesn't happen very often, so there's still a lot of NBS in solution as well. There's a lot of NBS in solution, and we're making more and more HBr. This reaction occurs between NBS and HBr to form succinimide and Br₂. How does that happen? HBr is an acid, which means it's an electrophile. It's an electrophile at hydrogen. Hydrogen has a partial positive charge, which means NBS must be acting as some kind of nucleophile. The question is where? If we look at a resonance contributor for this molecule, we can draw a resonance contributor that pushes a lone pair of electrons onto oxygen, giving oxygen a negative charge and nitrogen a positive charge. This shows us that oxygen is the most nucleophilic and most basic site in this molecule. So the preparation of Br₂ starts with oxygen grabbing a hydrogen from HBr, kicking out Br- as a leaving group, and that Br- can now come back in and attack bromine here to break the nitrogen-bromine bond, pushing electrons back onto nitrogen, and that forms this intermediate, and importantly, it forms Br₂. This is where we get the elemental bromine that we need for the second propagation step. This doesn't form succinimide directly though, so let's think about what's the difference between here and here. We have a nitrogen-carbon double bond. Here we have a carbon-oxygen double bond. Here hydrogen is attached to oxygen, and here it is attached to nitrogen. So we somehow need to move the hydrogen over, and we need to move the double bond over, and we are under acidic conditions. So the way that this works is we have more HBr. HBr is an acid, so we're going to use this molecule as a base. This time the most basic site is the nitrogen. That forms our nitrogen-hydrogen bond. We just need to get rid of the hydrogen and oxygen, and we can do that using Br-, and that will form succinimide and our Br₂ elemental bromine that we need for the second propagation step. These last two steps where we are trading the position of a hydrogen and a double bond, we call this process tautomerization. I talk more about tautomerization in another video, so I'm not going to expand on it here. The last thing we need to look at is why we get the regioselectivity that we do. Why do we form the most stable alkene rather than using the most stable radical? You can make a case for either scenario, that we should use the most stable radical or that we should form the most stable alkene. The product will win in this case. We know that from what we know about the mechanism already. If we look at an energy diagram, we can start to explain why. So if we look at an energy diagram just for the second propagation step, what we want to remember about these resonance contributors, which of these resonance contributors actually exists? Neither. Neither resonance contributor actually exists. That's a very important point with resonance. Recall, resonance contributors, none of them actually exist. It's not an equilibrium. It's not oscillating back and forth between the two. It's not sometimes this one, and then back, and then double bond moves. That's not what resonance is. Neither of these structures actually exist. The only thing that exists is the resonance hybrid. There's not actually two carbon radical intermediates. This is the same one carbon radical intermediate drawn twice. It's the same structure drawn two different ways. That's what resonance is. Neither resonance contributor exists. The only thing that exists is the resonance hybrid. So when we look at an energy diagram, we can start here at the intermediate, but there's only one intermediate. There's only one carbon radical intermediate. There's a partial double bond between each of those carbons and a partial radical on each of the two sides of the allylic system. We can form one of two products. We can form a less substituted alkene product, or we can form a more substituted alkene product. Each of these steps will have an activation energy, and we can see that there's a smaller activation energy to form the more stable product, and the more stable product is more stable. We get a larger delta H difference to form the more stable product. So given the choice, given this energy in this system, we will form the most stable alkene product possible. So this is why this reaction works the way it does. This is where we get Br₂ from, and this is why we form the most stable alkene product possible.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. It helps spread the word around the country. As always, don't forget to like and subscribe.